Okay, so my name is Nofar. I'll be talking about answering unions of conjunctive queries over relational databases. And this is joint work with my collaborators here. So before I go into the topic of this talk, I would just want to mention that recently in the past years, there is a surge of interest in fine-grained complexity related problems about enumerating answers to queries over databases. But so I just listed a few here from conferences in the past 2 years, but I'll be talking about things that are not listed here. So let's start by understanding our goal. We have a standard relational database. In this example, it's a database that describes TheoryFest. And we want to ask a conjunctive query. So this is an example of a conjunctive query. We want the XYs of the researchers' tables and the XZs of the attendance table, and we're only interested in the Y and Z, so we project the X out. So basically, the answer we want is to compute all of the elements of this set here. And the answer would be a list of the institutions and the workshops where the institution is represented in the workshop. So these are conjunctive queries, and unions of conjunctive queries is another form of interesting query language because it's equivalent to positive relational algebra. And unions of conjunctive queries are just some queries, and the answer to the union is the unions of the answers to the individual queries. So when I define the queries, I should probably mention that the lower bounds that we will see here only apply for queries with no self-joins, which means that you can't use the same relational symbol twice in the same conjunctive query. So if both of the tables there in the query are researchers and not researchers and attendants, then the lower bounds don't apply in this case. Okay, so we are treating every query as a problem. And we want to understand how hard this problem is. So the size of the query, we considered it to be constant. And the input is the database instance. So it's the tables, but the number of columns is considered constant, and we're using the RAM model. So what are our goals? First of all, one of the goals is to enumerate all of the answers. So we would say something like after linear time preprocessing, we want to get every answer after constant delay. And another task we're interested in is random permutation. So here we also want to enumerate all of the answers, but we have another requirement. We want to get the answers in uniformly random order. This means that in every point of time, if we look at all of the queries, at all of the answers that we produced so far, we want them to be a sample. And then we know, we can conclude something from that. So one way of achieving a random permutation is to separate it into different tasks. First of all, find a number of answers. Then we have some algorithm that generates a random permutation of the indices. And then we would have an algorithm that gets an index and returns answer number I. So that's why we're interested in the problem of random access to answers of queries. So given I, we want the ith answer, or we want a message out of bound if I is too big. Now, there's no constraints on the order that is assumed here as long as it's consistent. So we tell the algorithm, choose whatever order you want that's convenient for you, but just be consistent with that and give us the answers. And so random access can be seen as a way of computing the answers in a way that can give us uniformly random order or other requirements. And in this talk, we'll focus on random access and on enumeration. So let's see what we know about conjunctive queries first. So we have some dichotomy that tells us for each query, is it easy or hard, depending on its structure. So after linear preprocessing, queries with a structure that's called acyclic and free connex are easy. We can do random access with log n delay, enumeration with O of 1 delay, random permutation with a log n delay, and we can also do efficient counting, membership testing, and so on. And for other queries, we have two types of other queries. We have queries that are cyclic and not free conics, and queries that are not acyclic, so they're cyclic. And we can prove that they're hard, assuming hardness of Boolean matrix multiplication and hardness of finding hyperclicks in a graph. So to understand this, we need some definitions. An acyclic query, like this one over here, is a query that has a graph that represents it that satisfies these three properties. It has a node for every atom of the query. It's a tree. And for every variable of the query, if we only look at the nodes that contain this variable, we know they appear in a connected part of the tree. So for example, you won't have y here and here, but not in the middle. So this query is acyclic, but we also want the queries to be free conics. So it means that the free variables appear in a connected part of the tree. So roughly speaking, we want a subtree that contains exactly the free variables. So we only need the intuition to understand what's going on. So I'll go over the positive results quite quickly, only the intuition. If we have a query that's free conics, like this one here, and we have our database instance, we can find a join tree for this query, and then there is some process that runs in linear time and eliminates all tuples from our input that are not useful for the answers. And then we get this very compact representation of the input that we can use to efficiently solve all of the problems that we mentioned before. So we don't need to do things like generate large intermediate results that don't contribute to our output. Okay, now let's see the lower bounds. So for acyclic but not free conics conjunctive queries, like this one here, we use the assumption that Boolean matrix multiplication is hard. And we represent the matrices in our two relations here. So we encode the indices of the ones of each matrix in the corresponding relation. And then this query computes this result that we use to represent the indices of the ones in the answer. And basically, this is exactly the definition of Boolean matrix multiplication. We have 1 in index 1, 2, and it can be explained by the ones in indices 1, 2, and 2, 2. So if we can solve this query with O of m pre-processing, where m is the number of ones in the input and output, and then logarithmic delay, then it means that we solved matrix multiplication in m log m time. So if we assume we can't solve matrix multiplication in this time, it means we don't have a log delay algorithm for enumeration with any order. It doesn't matter the order. And if we assume that we cannot solve Boolean matrix multiplication with m time, then it means that we don't have a constant delay algorithm. So basically, the reason it's hard is because the time we give the query is the delay per answer, and we don't have to go over all explanations of the answers. And every answer can have several explanations here. Okay, what about cyclic queries? So to show that cyclic queries are hard, we need the assumption that we cannot find hyperclicks in a graph. So we cannot find a set of k nodes such that each k minus 1 of them appear in an edge. And then for every query, we would need this assumption for a different k. So for example, for this query here, we need this assumption for k equals 3, so we need to assume that we cannot find triangles in linear time in the number of edges. So if we start with a graph where we want to find triangles, we encode all three relations with the edges of the graph, and then this query just finds triangles. That's what it does. So if we assume we cannot find a triangle in linear time, it means that we cannot find a first answer to this query in linear time, and in particular, we can't do any of this after linear preprocessing and such small delay. So that's what we have for conjunctive queries. And now our task is to see how this extends to unions of conjunctive queries. So for enumeration, we know that a union of two easy queries is always easy. Now, we can't just, if we have two black boxes that enumerate two sets, we can't just run one and then run the other, because we can have duplicates. And even if we save the duplicates and then just don't print them again, we can have a long time where we only see things we've seen before. And then the delay is not constant or logarithmic anymore. But what we can do is this nice trick. We enumerate all of the answers to the first problem, and then whenever we see a problem, we check if it's in B over there. If it's not in B, we print it. If it is in B, we just print something out of B, the next element in B. And when we're done, we print everything else out of B. So basically, this line over there prints A minus B, and the other two lines print B. And since it's a partition of what we want, it prints exactly what we want, with no duplicates and very efficiently. Okay, so for enumeration, a union of two easy problems is easy. Now we want to know what happens with random access. And actually, we show that for random access, a union of two easy queries can sometimes be hard. And here's an example. These two queries are both easy. They're free connex. They contain just two relations. There are no projections. So they're very easy to solve. If we look at the intersection of these two queries, we need answers that satisfy the condition on R, on S, and or on T. This is the intersection, and it's exactly the cyclic query we saw before. So we know that we cannot find the first answer if we cannot find triangles in a graph in linear time. Now, assume by contradiction that there is an efficient random access algorithm for the union. Then since Q1 and Q2 are independently easy, we can find a number of answers to Q1, find a number of answers to Q2, and then ask the random access algorithm for answer number Q1 plus Q2. And then we see if it tells us out of bound or not. If it tells us out of bound, we know that the size of the union is strictly smaller than the sum of the individual sizes, which means that there is something in the intersection, and this contradicts the fact that we cannot find triangles in a graph efficiently. So a union of two easy queries is not necessarily easy. And here is an open problem. If we look at all of the queries in the world, we know that when we can do efficient random access, so for example, random access with log time after linear time preprocessing, then we can also do random permutation. If we can do random permutation, we can do enumeration, because random permutation is just a form of enumeration. And we know that there is this problem that I showed you that has efficient enumeration but doesn't have efficient random access. And the query is, where is random permutation in all of this? Is it as hard as random access, or as hard as enumeration, or somewhere in between? And a good first step would be to know if this example can be solved, if we can find a random permutation for it in log delay. Now we know we can do it in expected log delay, but can we do it in actual log delay? Another interesting question is what happens when the union contains a hard query? And here's an example. The first query is hard, it's not free connex. So there's this R2, R3 part over there. We can reduce matrix multiplication there. And the second query is easy. It's free connex, it's just two relations and no projection. And the projections are in the side, they don't bother us. But if you look carefully, you'll see that everything that's an answer to the first query is also an answer to the second query, because the first query just has another restriction. This means that the entire union is equivalent to the easy query. So this is a union that contains a hard query. That's easy. But that's not very interesting because this query is redundant. So it makes sense to look at non-redundant unions. And it was claimed in the past that non-redundant unions that contain a hard query are always hard. And we were actually able to refute this claim. And we showed that there are some unions that contain a hard query that are easy. Not only that, there are unions that contain only hard queries, and still they're easy. So this example over here, I don't think I have enough time to explain it properly now, but basically there are two queries over here. In one of them, the hard part is the first, and in the second one, the hard part is the second. And we can solve them in a way that we can find a subset of the answers of the first query, then this helps us compute all of the answers to the second query, and then this helps us to compute the rest of the answers to the first query. Now you can see that even though you can reduce matrix multiplication to each query individually, you can't do that when the union is together, because then basically you would have too many answers, and you compute the matrix multiplication, but it takes too long, so it doesn't contradict anything. So there's an open problem here too. We have some results, some lower bounds about unions, but we don't have a complete dichotomy about all unions, and we would like to know what categorizes unions of conjunctive queries that are easy with respect to enumeration. A first step would be to solve some specific examples of queries that we don't know if they're easy or hard, and actually the last section of our paper contains a lot of such examples. So if anyone wants to get more information about this or discuss the open problems, I'll be standing next to my poster at the end of this session. Thank you.